Imagine peering out into the inky blackness at the very edge of our known solar system,
Way out there.
past Neptune, past the Kuiper Belt, into this vast, dark, unexplored territory.
Mm-hmm.
And maybe, just maybe, out
Mm-hmm.
there, lurking in the cosmic shadows, is something massive.
Something we haven't seen.
Exactly, something we can't see yet, but whose gravitational whispers are hinting, maybe, that it's there. Is it real?
Huh?
Or just a ghost conjured by strange orbital alignments? Welcome to the Cool, Weird, and Possible.
And today, yeah, we're diving into a mystery that really does feel ripped straight from a sci-fi novel.
Right.
But it's actually grounded in some pretty cutting-edge astronomy and mountains of data you've shared with us. We're talking about the hunt for a hypothesized ninth planet in our own solar system, often called Planet Nine.
You sent us this fascinating stack of sources, research papers, articles, even some really intriguing discussions online. And it all points to this incredible possibility that our solar system might be bigger and, frankly, weirder than we thought.
Definitely weirder.
So our mission in this deep dive is to sift through all this evidence you've compiled and try to figure out what's actually going on out there.
Consider this our joint investigation, basically. We're looking at the latest information, trying to piece together the clues that have led scientists to, well, propose this massive unseen object.
All right, Mr. Science, let's get to the bottom of this cosmic whodunit. Where did the suspicion first fall on a hidden planet? Like, what were the first clues that started this whole chase?
Okay, so it all really kicked off when astronomers started studying what's happening way out beyond Neptune in that distant region we call the Kuiper Belt.
Right, the icy stuff.
Exactly. And specifically, they started looking very closely at a population of extremely distant icy bodies. They're known as extreme transneptunian objects, or ETOs for short.
ETNOs.
Yeah.
Okay, and they noticed something weird about them.
Statistically speaking, yes. Very weird. I mean, you'd normally expect these objects orbiting so incredibly far out to have their paths, their orbits, oriented pretty randomly in space.
Like scattered all over.
Yeah, exactly. But studies, notably by researchers like Trujillo and Shepard starting around 2014, and then probably most famously by Konstantin Batygin and Mike Brown in 2016, they found something completely different in the orbits of a specific group of these ETNOs.
The sources you sent definitely mentioned a strange clustering. What does that actually mean for their orbits, though?
Okay, think of it like this. If you plotted the points in space where these distant objects make the closest approach to the sun, their perihelia, those points aren't scattered randomly. They tend to cluster together in one general direction in the sky.
Huh. So it's like their orbits are all kind of facing roughly the same way.
That's a good way to put it, like a bunch of cosmic arrows all pointing in generally the same direction instead of, hitting all over the target board.
Okay, got it.
And it's not just the direction either. Their orbits also show a similar significant tilt compared to the relatively flat plane where the main planets Earth, Mars, Jupiter orbit the sun.
A tilt. How much of a tilt are we talking?
Well, one source talks about this clustering, suggesting the overall plane of these distant objects might be tilted by about 20 degrees relative to the main planets. Another mentions the potential shepherding object itself might have an orbit tilted by around 30 degrees. It's significant.
So it's not just that their paths line up directionally, but they're also collectively angled away from the solar system's main highway, so to speak.
Precisely. And the odds of, half a dozen or more really distant objects happening to line up like this, both in direction and tilt, just by chance, they're incredibly low.
Vanishingly small, probably.
Yeah, probabilities that make scientists sit up and say, okay, something gravitational is almost certainly influencing these objects. Something massive must be out there kind of corralling them.
So these distant icy rocks are basically unwitting witnesses. Their strange orbits are giving testimony to some unseen force pulling the strings.
That's a really good analogy, actually. They're like cosmic breadcrumbs, potentially leading us toward whatever's doing the pulling.
And it's not just those clustered ETNOs, right? The sources mention other weird things, too.
Right, that's important. The Planet 9 hypothesis also seems to provide a pretty plausible explanation for a few other oddities out there. Things like certain Kuiper Belt objects with extremely high orbital inclinations almost perpendicular to the main plane.
Whoa, perpendicular.
Yeah, and even some unusual objects called centaurs that orbit the sun backwards relative to almost everything else.
Backward. Okay, now that's properly weird. So this Planet 9 idea, it doesn't just explain one anomaly. It's potentially like A key that unlocks several different puzzles at once.
That's exactly the point made by proponents like Konstantin Batygin. He's quoted in these sources saying there are actually, I think, 5 different lines of observational evidence that the Planet 9 hypothesis seems to address quite neatly.
5. Wow. So if you take Planet 9 out of the equation, you're left with 5 separate, weird things that somehow need their own individual, maybe unrelated explanations.
That's the argument, yes. And it's a compelling one. The hypothesis offers a single sort of unifying explanation for these seemingly disparate orbital behaviors we're seeing way out at the fringes of the solar system. It strongly suggests that something significant, something with the substantial gravitational pull, is out there shaping these distant orbits.
Okay, the evidence for something being out there sounds pretty strong then, based on what you've pulled together. It's not just one thing, it's multiple strained orbital patterns all kind of pointing somewhere.
Right.
So if this gravitational shepherd is a planet, what do the scientists hypothesize it's actually like? What's its cosmic profile? Give me the specs.
Okay, so based on the amount of gravity needed to sculpt those ETNO orbits the way we see them, the models give us some predicted characteristics for this potential Planet 9.
How big are we talking? Like Earth-sized? Jupiter-sized?
Somewhere in between, actually. The estimates for its mass generally fall in the range of about 7 to maybe 17 times the mass of Earth.
Okay, 7 to 17 Earth masses. So that puts it firmly in the category of a super-Earth or maybe a mini-Neptune. Definitely not a dwarf planet like Pluto.
Absolutely not. It's predicted to be significantly more massive than Earth, but yeah, smaller than our gas giants like Jupiter or Saturn. In terms of physical size, it's thought to be roughly the size of Uranus or Neptune.
Ice giant territory.
Exactly. But its orbit, that's where things get really wild compared to the planets we know.
Yeah, I'm guessing it's not exactly hanging out near Earth or Mars, is it?
Not even close. The predicted orbit is highly eccentric.
Meaning very oval-shaped, not circular.
Very elongated, yeah. Not a neat circle like Earth's orbit. And it's incredibly far out. The estimated average distance from the sun varies a bit in the sources, but it ranges anywhere from, say, 250 AU up to maybe even 1,000 astronomical units.
Whoa, hang on. Remind me, an AU is Earth's distance from the sun.
Right, about 93 million miles or 150 million kilometers. And Neptune, our farthest known planet, is only about 30 AU out.
30. So Planet 9 could be 10, 20, maybe even hundreds of times farther from the sun than Neptune. One source mentioned maybe 400 to 800 AU as a likely range.
Yes, some of the more refined models based on the ETNO data narrow it down to that sort of range at those distances. Well, sunlight is incredibly faint. This thing would be extremely cold and very, very dark.
And its orbit is also tilted, right? That explains the tilted ETNOs.
Exactly. The hypothesis requires its orbit to be significantly tilted relative to the main plane of the solar system, maybe around 30 degrees, which naturally explains why it would pull those distant objects into similarly tilted orbits.
So we're picturing this decent-sized planet, maybe like a smaller Neptune, swinging way, way out there on this incredibly wide, tilted oval path through the darkness. Which, okay, begs the question, how in the universe would a planet even end up there?
That's another really fascinating angle explored in these sources. One quite intriguing theory highlighted in a study from the Planetary Science Institute suggests its origins might actually tie back to the chaotic early days of our solar system.
The very beginning.
Yeah, back when the sun and its planets were still forming within a stellar birth cluster.
A stellar cluster. You mean like our sun had siblings nearby? Loads of other stars.
Billions of years ago, yeah, the sun likely formed in a pretty crowded stellar nursery. Think thousands of young stars, all packed relatively close together. It would have been a gravitationally messy environment.
Like a cosmic mosh pit. I like it.
Yeah, pretty much. And giant planets forming in that kind of environment can gravitationally interact, scatter each other around quite violently. Sometimes a planet can get a huge gravitational kick from another giant planet and get flung outwards onto a very distant path.
Kicked right out of the solar system entirely.
Sometimes, yes. But the theory is, if this scattering happens while the solar system is still inside that dense stellar cluster, the gravitational pull from nearby other stars in the cluster could actually intervene. Before the scattered planet completely escapes our sun's gravity, the combined pull from those surrounding stars could sort of nudge it, stabilize it, and essentially trap it in a very distant, but still gravitationally bound, orbit around its own star, our sun.
Okay, hang on. So it gets kicked out of the inner house, but the neighbor's gravity kind of ropes it in, and keeps it from leaving the neighborhood entirely. It just ends up living way out on the cosmic back 40.
That's a fantastic analogy, and the simulations shown in some of this research suggest that solar systems forming in these clusters can actually be quite efficient at trapping planets scattered outwards like this. Maybe, 5 to 10% of planets that get scattered could end up in these wide, stable, but distant orbits.
5 to 10%, that's surprisingly high.
It is. So while finding a planet way out there might sound like a totally crazy idea, it's not theoretically impossible. It could actually be a natural byproduct of how planetary systems like ours are born in these crowded stellar nurseries.
Wow. So Planet 9 could be like a relic from the solar system's wild teenage years, preserved way out in the cold.
In a way, yeah. A reminder of that chaotic beginning.
But okay, even with all this gravitational evidence pointing to something massive and a plausible story for how a planet could get there, a planet isn't the only thing that could cause those effects, is it? I definitely saw mention of some even weirder possibilities in the sources you sent.
You're absolutely right. And good science demands exploring alternatives. While a planet is often considered the, let's say, simplest explanation for the combination of observed anomalies, scientists have definitely explored more exotic alternatives. Any good detective considers all the suspects, right?
Right, like the one that sounds like pure science fiction, a primordial black hole.
Yep, that one's definitely been suggested. The idea is that the gravitational source pulling on the ETNOs might not be a planet, but a primordial black hole.
Primordial meaning, formed right at the beginning of the universe.
Exactly, not from a collapsing star, but from density fluctuations in the very early universe. And it would need to have roughly the same mass as predicted for Planet 9, so maybe 5 to 10 times the mass of Earth.
Okay, a black hole with the mass of several Earths. That sounds terrifying. How big would it physically be?
That's the wild part. According to the physics, a 10 Earth mass black hole would actually be incredibly tiny. We're talking maybe twice the size of a baseball.
Get out. Twice the size of a baseball, but with the mass of 10 Earths squeezed inside. That is ridiculously dense.
Extremely dense.
And I imagine also incredibly difficult to actually spot out there.
Extremely difficult, yeah. It wouldn't emit any light of its own, obviously. Maybe some faint radiation if it happened to accrete gas or dust, or maybe detectable through gravitational lensing if it passed in front of a star. But finding a solitary tiny black hole at hundreds of AU, that's a huge observational challenge.
So it's not impossible, as one source put it, but just way harder to find than a planet reflecting sunlight, even faintly.
That's a major factor, yes. Scientists tend to gravitate towards hypotheses that are more readily testable and verifiable with current or near-future technology. While a primordial black hole isn't ruled out theoretically, finding direct proof would be significantly harder than finding a faint planet that reflects sunlight or emits its own faint thermal radiation.
Okay, what about those other alternatives mentioned? Something about a ring of material or dark matter.
Yeah, those pop up too. Some sources briefly mention ideas like maybe there's a distant unseen disk or ring of smaller icy bodies out there, and their collective gravity is doing the shepherding. Or even a clump or concentration of condensed dark matter somehow lurking in the outer solar system.
So not a single massive object, but like a diffuse ring or maybe a weird cloud of stuff exerting gravity?
Potentially. The issue there is that these hypotheses often require more complex arrangements or fine-tuning of the mass distribution to reproduce the specific pattern of orbital clustering and tilting we see in the ETNOs compared to just having a single massive object like a planet doing the work. The planet model tends to be simpler in that regard.
And I saw the term MOND pop up in one of the sources. Modified Newtonian dynamics? What's that about? Isn't that usually about galaxies?
It usually is, yeah. MOND is an alternative theory of gravity. It basically suggests that gravity might behave slightly differently than standard Newtonian physics predicts over very large distances, or, crucially, at very low accelerations, like those experienced by stars in the outskirts of galaxies.
Okay.
It was originally proposed to explain galaxy rotation curves without needing hypothetical dark matter. Because Planet 9 hasn't been directly detected yet, despite the searches, some have speculated. Well, maybe the orbital anomalies we see in the Kuiper Belt aren't due to its hidden mass at all. Maybe they're the first hint that MOND effects are actually significant even on the scale of our own solar system.
So instead of a hidden planet, maybe gravity itself is just acting differently, way out there. That's a truly wild thought.
It is pretty profound, yeah. But MOND is a complex theory, and making it work consistently for everything we observe, including the very specific clustering in the Kuiper Belt, is quite challenging. For now, most researchers working directly on this problem still consider the hidden mass hypothesis, specifically a planet, as the most straightforward explanation that fits the current observational evidence best.
Okay, so the science community is definitely exploring all the weird possibilities, which is cool. But the planet theory is still the lead detective's #1 suspect. Which brings us to the really exciting part. The Great Hunt itself. How are they actually trying to find this elusive object hiding out there in the vastness?
This is where the detective work gets really intense and honestly pretty impressive. Scientists are engaged in this massive, multi-pronged search effort. They're sifting through everything from decades-old archival data from past surveys to using images from the most powerful telescopes scanning the sky right now.
Like going through old case files and looking for clues that previous investigators missed.
Exactly like that. A prime example mentioned in the sources is the Pan-STARRS 1 survey, or PS1. This was a telescope in Hawaii that surveyed a huge chunk of the sky over several years. It collected, get this, over 1 billion initial detections of objects.
1 billion. Good grief. How do you even start to find one faint, slowly moving object in that absolute haystack of data?
It's a monumental data science challenge, no question. They have to apply really sophisticated filters first, things based on, image quality, how point-like the detection looks, filtering out known asteroids and artifacts that might reduce the billion down to maybe, say, 244 million potential detections, as one source noted.
Still huge.
Still huge. Then they use complex algorithms to look for multiple detections of the same object appearing in different images taken at different times, but along a path consistent with an orbit.
Because a distant planet, even a very distant one, would still show some movement against the fixed background stars over time.
Precisely. Unlike stars, which basically stay put from our perspective over human timescales, any object within our solar system will appear to move slowly across the sky, night to night, year to year. The big challenge with archival data like PS1, though, is that the observations weren't necessarily designed specifically for finding this kind of object very faint, very slow-moving.
Right.
So an object often needed to be detected multiple times. One source mentioned maybe 9 or more times over the entire multi-year survey for scientists to reliably link those detections, confirm it was a real moving object, and calculate a rough orbit.
Okay, so you need a lot of sightings in that old data, whereas if you were doing a targeted search, maybe looking at the same patch of sky on 2 consecutive nights, you might only need 2 detections to spot that telltale shift, that parallax motion.
Exactly. That's a different search strategy, a targeted search, versus sifting through massive archival data sets that weren't optimized for this specific task.
How do they even know if their search methods are sensitive enough? Like, how do they know they're not just missing Planet 9 because it's too faint or their software isn't good enough?
That's where they use techniques involving reference populations and calibration. It's pretty clever. They basically simulate thousands, maybe millions, of hypothetical Planet 9 objects.
Fake planet.
Fake planets, yeah. With all the predicted parameters, different possible masses, orbits, locations in the sky, and brightnesses. Then they digitally inject these fake objects into the real survey data.
Okay.
And then they run their entire search pipeline, their detection algorithms, on that data containing the fake planets and see how many of them their software successfully recovers or finds.
Huh. It's like planting fake evidence at a crime scene to test if the detectives are any good.
That's essentially what it is. It tells them what percentage of the predicted parameter space, basically, the range of possible locations and brightnesses where Planet 9 might realistically be their search is actually sensitive enough to cover.
Smart. So what have those tests shown? How much ground have they covered?
Well, the sources mention that combining the data from PS1 with other major surveys like the Zwicky Transient Facility, ZTF, and the Dark Energy Survey, DES, has allowed scientists to rule out, get this, about 78% of a standard reference population based on the prevailing Planet 9 models.
78% ruled out. That's actually huge. So they've significantly narrowed down where it could be hiding.
Absolutely. It means a large portion of the sky, down to a certain faintness limit, has been searched pretty thoroughly, and Planet 9, at least as currently modeled, wasn't found there. But, and this is a really key but significant unsurveyed areas still remain.
Where? What are the tough spots?
Particularly areas near the plane of the Milky Way, the galactic plane, and also regions at low declinations, meaning close to the celestial equator as seen from certain observatories.
Why are those areas harder to search?
Well, the galactic plane is just crammed full of stars, millions and millions of them. Trying to spot one faint moving dot against that incredibly crowded, bright background is extremely difficult. It's like finding a specific needle in a galaxy-sized pile of needles.
Okay, yeah, I can see that. And low declinations.
That can be challenging just based on an observatory's location on Earth and how low that part of the sky appears, affecting visibility and image quality, especially near the horizon.
Gotcha. Were there any specific targeted searches mentioned in the sources, like looking really hard at one small patch?
Yes, one source discussed a targeted search conducted in a specific region of the sky known as the Cieno S14 field. It was a relatively small area, only about 98 square degrees on the sky.
Why there?
It was actually motivated by trying to find the origin of an interesting interstellar meteor that landed on Earth. But they used techniques specifically designed to detect the parallax motion of nearby objects by comparing images taken on consecutive nights. They searched down to a sensitivity limit of about magnitude 21.3.
21.3. That sounds pretty faint.
Yeah.
Did they find anything that looked like Planet 9 in that specific spot?
Nope. No credible candidates matching the expected motion and brightness of Planet 9 were found in that particular targeted field. So that tells us Planet 9 probably isn't hiding in that specific patch of sky, at least not bright enough to be seen at that depth via parallax over just a couple of nights.
Okay. What about using older data from space telescopes? I think I saw IRAS and Akari mentioned infrared satellites.
Right, that's another approach people have tried, leveraging data from all-sky infrared surveys done by space telescopes like IRS back in the 80s and the Japanese Akari satellite more recently.
Hmm.
Infrared is good for finding cool objects. One study reportedly used data spanning 40 years from these and other surveys to look for objects moving very slowly at rates consistent with something extremely distant.
And did they find anything promising?
They apparently found one potential candidate object showing movement of about 3 arc minutes per year, which is roughly in the ballpark for something very far out.
3 arc minutes per year. That's incredibly slow movement.
Extremely slow. And the source states this candidate is estimated to be quite far out and maybe fix the predicted mass and size range, generally consistent with some Planet 9 models. However,
There's always a however.
there's always a however. The data from those older infrared surveys, while covering the whole sky, wasn't really optimized for precisely tracking solar system objects over long periods or mapping their orbits accurately. The data was described as insufficient to fully confirm the object's identity or plot its complete path. Plus, the study was apparently still awaiting peer review when one of the sources was written. So, an intriguing hint, perhaps, but definitely not a confirmed detection. Still needs follow-up.
Okay, so they're throwing everything they've got at this old space data, massive ground surveys, targeted searches, and they've done an amazing job basically mapping out where Planet 9 isn't likely to be based on the models.
Exactly. The search has been incredibly successful in that respect, ruling out large swathes of the possibility space.
But no definitive eureka moment yet. The most likely remaining hiding spots seem to be those really tricky areas.
That's pretty much the current situation. The most plausible remaining locations are those challenging regions near the galactic plane or areas that just haven't been surveyed deeply enough yet. They require deeper, more persistent, more systematic surveys.
Which brings us neatly to the future, and the telescope that seems to be everyone's big hope in this whole saga, the Vera C. Rubin Observatory.
Ah, yes, Rubin. This observatory down in Chile is widely considered the absolute game changer in the hunt for Planet 9. It actually began its commissioning phase in April 2025, and it's expected to start its full decade-long main survey, the Legacy Survey of Space and Time, or LSST, very soon.
Okay, so what makes Rubin so special? Why is it potentially the key to finally solving this mystery?
It really comes down to its sheer scale and its purpose-built design. It's specifically built to do one thing incredibly well: scan almost the entire southern sky over and over again every few nights for 10 years straight. It has this enormous 8.4-meter primary mirror and the largest digital camera ever built for astronomy. We're talking 3.2 gigapixels.
3,200 megapixels. That's insane. How does that help find one faint object way out there?
By repeatedly scanning that huge area of sky to unprecedented depth, Rubin will be incredibly sensitive to faint moving objects. It's expected to just revolutionize our census of the solar system. The estimates are it could increase the number of known asteroids, comets, and Kuiper Belt objects by perhaps tenfold.
10 times more objects.
Yeah. which means finding vastly more of those distant ETNOs, the very objects that provide the gravitational evidence for Planet 9 in the first place. With a huge population of those objects, and Rubin tracking their orbits precisely over a decade, scientists will get an even tighter constraint on whatever gravitational influence is shaping them.
So more breadcrumbs and much clearer paths for them to follow.
Exactly. And crucially, Rubin is expected to be sensitive enough to directly detect an object as faint as Planet 9 is predicted to be, even at its most distant possible locations, and even in those challenging areas near the galactic plane that have been tough for previous surveys.
Wow. So the astronomers working on this must be pretty optimistic then.
Extremely optimistic. Scientists like Scott Shepard, who's been heavily involved in the search, estimate a very high probability, something like 70 to 80%, of finding Planet 9 with Rubin if it exists within the currently predicted range of possibilities.
70 to 80%. That's confident.
And Mike Brown, one of the originators of the modern Planet 9 hypothesis, sounds incredibly confident too. One source quotes him as having extraordinary confidence and even suggesting it could potentially be found within the first year of Rubin's full science operations.
The first year. Okay, that's bold.
It tells you the level of expectation riding on Rubin. It's designed specifically to cover much of the remaining sky where Planet 9 could plausibly be hiding, including many of those harder-to-survey regions. The next few years, as Rubin ramps up and starts collecting more and more data, they are absolutely critical for this search. We might finally get an answer.
Okay, so the stage is well and truly set. The circumstantial evidence is there in the orbits, the previous searches have narrowed down the possibilities dramatically, and now the ultimate cosmic detective tool, Rubin, is coming online. Just imagine that moment. Rubin spots it, tracks its motion over a few nights, confirms it's the real deal. What happens then? What happens after Planet 9 is actually found? Mike Brown said the real excitement begins then.
He's absolutely right. Finding it, getting that initial confirmation, that's really just the first step. Once its location is pinned down, you'd see an immediate, massive pivot from astronomers all around the world, and probably using space telescopes too. He says they'd turn every telescope on the planet and off the planet towards this new object.
To basically figure out absolutely everything they possibly can about it.
Precisely. The immediate goal would be to observe it constantly, track its motion to determine its full orbit with incredible precision. But beyond just the orbit, they'd start intense characterization studies.
Like what?
Trying to see if it has any moons orbiting it, or maybe even rings like Saturn or Neptune, analyzing the light reflected from it or any heat it emits to understand the composition of its atmosphere, if it has one, and maybe even its surface properties.
Finally seeing the face of this gravitational ghost that's been haunting the outer solar system. That would be absolutely astounding.
It would completely rewrite our understanding of the solar system's formation and evolution, a genuine scientific revolution, and then, inevitably, the really big thinking starts. The possibility of actually sending a space probe out there for a closer look.
A probe all the way out there. We're talking hundreds of AU. That sounds, well, bordering on impossible with current tech, at least in any reasonable time frame, right?
Right. Oh, the sources definitely acknowledge the immense challenges involved. Getting a spacecraft that far out requires incredible speeds, maybe using gravity assists from Jupiter and the Sun. Even with advanced propulsion concepts being studied, the travel times could easily be, 100 years or even more.
A century-long journey just to get there.
Exactly. And then you have the problems of powering the instruments for that long and communicating back to Earth over such unimaginable distances. The signals would be incredibly faint and take decades to arrive.
Wow. It really drives home just how incredibly vast the solar system is, even just our own backyard, relatively speaking.
It absolutely does, but the potential scientific payoff, getting actual close-up images, taking detailed measurements of this entirely new type of planet in our own system would be just immense. As Mike Brown put it, once the target is actually identified and we know exactly where it is, the scientific motivation might make such an audacious mission too hard to resist, despite all the difficulties. It becomes a kind of generational project for humanity.
So, to bring our deep dive kind of full circle here, the search for Planet 9 stands as one of the most compelling active mysteries in astronomy right now. We have this strong, persistent, indirect gravitational evidence coming from the weird orbits of those distant icy objects.
Right. And numerous ongoing and completed surveys have cleverly used that evidence to really narrow down the potential hiding places, ruling out a huge portion of the sky where it could have been, according to the models.
And now, the arrival of the Vera C. Rubin Observatory represents the most promising development yet. It seems truly poised to either finally find the planet or perhaps gather enough negative data to definitively rule out its existence, at least in the most likely predicted forms and locations.
The next few years are genuinely critical. We might finally uncover this hidden giant lurking in the outer darkness, or the continued lack of detection, even with Rubin's power, might force scientists to seriously reconsider the very nature of those gravitational anomalies we observe. Maybe start taking some of those weirder ideas more seriously.
It really is a cosmic detective story, playing out in super slow motion, way, way out on the frozen fringes of our solar system. Whether Planet 9 is ultimately found, proving our cosmic neighborhood is even stranger and more wonderful than we thought, or whether the mystery endures, forcing us to explore even wilder explanations about gravity or the universe. What is this persistent human drive to search for the unknown, for the hidden things lurking just out of sight? Tell us about ourselves, and about the true limits, maybe, of our current understanding of the cosmos. It's definitely a question worth pondering as we wait for the skies, hopefully soon, to reveal their secrets.